Okay, so tonight I thought we'd talk about low-cost spectrum analyzers and look at some of the pros and cons about using something like that and see if it kind of might meet your needs. Spent a lot of time talking about the that low-cost VNA, vector network analyzer, that you can get for anywhere from 60 to 150, $170, and how that's kind of revolutionized things. So tonight we're going to talk a little about low-cost spectrum analyzers, not the big dudes. How does a spectrum analyzer differ from an oscilloscope? It's kind of interesting. I keep running into people that think that an oscilloscope is a spectrum analyzer. It's not, and I'll explain why. And it will give you a better perspective of what a spectrum analyzer actually does. Do these low-cost spectrum analyzers really work? Well, we'll learn. I mean, it's not like, chucking out a couple $1,000 for a big dude, but it does. There's some worthy things to consider there. So, what can I do with this low-cost spectrum analyzer? Why should I have one of these pieces of equipment for my test bench? And mind you, this program is not going to get into technical stuff. It's not going to tell you how to use that spectrum analyzer. It's going to give you some top level ideas to see if it's something that you want to consider as far as acquiring to put on your test bench. So to open up, this is just a fuzzy picture of what a good old oscilloscope looks like. So there's just two sinusoidal waves, actually three sinusoidal waves there. One's a sum of what's going on there. And this is just a low-cost modern digital oscilloscope that has a whole lot of neat features built into it and for a very, very reasonable price. So what is an oscilloscope? It displays set electrical signals at a certain time. So time is displayed in the x-axis, that's going in the horizontal position. Signal amplitude, the signal strength, is shown in the y-axis, that's the vertical axis. So signal amplitude is displayed in volts. Very important here. Think about that. Amplitude is strictly displayed in volts for an oscilloscope. So displaying, it actually displays a plot of voltage over time. So whatever signal you're looking at, it displays whatever that voltage is over some amount of time, whatever that sweep time. So understand, this guy here is really not built for trying to track down RF issues, radio frequency issues. So here's another kind of picture of what's going on here. So time is displayed in that horizontal direction, and the amplitude is being displayed in the vertical. And understand that amplitude on oscilloscope, it can be a positive amplitude, it can be a negative amplitude, and it can be both positive and negative. So see that little arrow on the left-hand side there, that's probably representing the 0 voltage crossover point. So here's a fancy Vectrum spectrum analyzer, and this guy just happens to be showing a IMD pattern, intermodulation distortion there, and shows what's going on there. So when you first look at this and you think about all the things that this guy can do, it doesn't look like very many buttons, but you got all kinds of menus, all kinds of different ways of getting into all the little secrets that's stored inside this box here. But a typical spectrum analyzer, something like this, will go from anywhere from, at the bottom end, maybe $1,300 to about $7,000. In the old days, these things used to run for $30,000 to $60,000. Big difference. So the kind of guy we're going to be talking about is this little dude here. So, or in this general category. So this is a little guy that's on the market there called a Tiny SNA spectrum analyzer. And this will give you some very basic information, actually a little bit more than basic. It'll give you some good information on what you can get from a spectrum analyzer. So it's okay for doing some basic testing, and we'll talk about what that is. So what is a spectrum analyzer? Displays and measures a signal amplitude, the strength, excuse me, let me try that over. Displays and measures a signal amplitude, the strength of the signal as it varies by frequency. So that's a big mouthful of words, and let's see what that mouthful of words means. Frequency appears in the x-axis. So the frequency that's being captured is going in the x-axis. Signal amplitude is displayed in the vertical axis, very, very similar to what goes on in an oscilloscope, but there's a major difference here. Frequency being measured is usually is user selectable. So you can select a start frequency and a stop frequency. So what the frequency is you want to sample. You also have other user modes where you can select, like, let's say, the center frequency that you want to sample, and then you can select the width of how much you want to capture. So there's lots of flexibility in the area that you want to capture. But basically, you're taking a snapshot, you're taking a picture of a range of frequencies, the start and stop frequencies. The signal amplitude is displayed in decibel, not voltage. So this is in a logarithmic scale. And I think all of us ham radio operators know that, when we talk about amplitude, when we talk about power, we always talk about that in decibels. So big change here. We think of that vertical axis in decibels, which is exactly what we want for doing our craft. So this device is well suited for RF exploration. So here's a really cool graph that helps you get your head around a little bit about the difference between an oscilloscope working in the time domain as opposed to a spectrum analyzer working in the frequency domain. So there at the very bottom of that, on the left side there, you have a window, and that shows when it looks at things in the time domain on what it's going to capture as that picture, looking at just one very small slice out of that whole big domain out there. It's called the time domain. Now, if you're a spectrum analyzer, move over to the right side. There you're going to catch all the different frequencies, the amplitude of all those different frequencies, and it's going to be spread out over the frequency domain. So that gives you a really cool picture about thinking about the difference between an oscilloscope and a spectrum analyzer. And you can get a better idea about why it's such a better fit for everything that we do in the ham radio community. So spectrum analyzers. So what does a spectrum analyzer measure? So it'll display spurious signals. So if something's not supposed to be there, it'll display it if you want it or not. Complex waveforms. So, we have a lot of digital type of stuff that we do these days. And so there may be other waveforms where we're mixing things, and that'll display that. Rare short durations of events, like something like a little spike or a little noise. Same thing with a transit signal. It'll capture that kind of stuff. Remember, the spectrum analyzers you get today is something that works digitally. It's a digital scope. So once you capture something, you can freeze it, you can save it to memory, you can go back and later on pull that memory image back up, and you can look at it again. You can also do some level of drilling in, trying to isolate the problem to some level. One thing you can't do is add information. You can't add information for what you've captured and saved in memory. All you can do is narrow the scope and what you're trying to look for, and you still have some limits on what you can take and narrow down. So it's cool for like capturing bursts of transmission, as sometimes you can set up triggers in there to try and catch those kind of bursts or those glitches, and then that can save it, and then you can go through there and analyze that thing. So once you got it saved on your scope there and saved, you can go back through there and you can pillage and plunder through it, try and figure out what's really going on. Go show if a strong signal is masked by a weak signal. It can help examine things that have huge dynamic ranges, so you can capture things that have a large spectrum, a large footprint, and then you can go through there and take it apart little piece by piece. Pretty cool. More things you can do it. So looking for harmonic distortion. This is one of the things that we're always being concerned about, looking for different kinds of distortion, things that may be audio type of distortion, it may be mixing of RF. One of the things for mixing for RF, and that's when we talk about IMD, intermodulation distortion. This is the go-to tool for looking for IMD distortion. We also have lots of problems with RFI, radio frequency interference. This is a really cool tool for tracking down RFI. A lot of people like going out there with their AM radio to try and listen to power poles, listen to the neighbors' grow lights. But remember that an AM radio is really cool in what it does, and it's portable, but it's only going to show you what's going on the AM frequencies, from 550 to what, 1.4 megahertz or 1.3 megahertz, 1.35 or whatever it is. So with a portable hand spectrum analyzer that's battery operated that you can carry around with your hand, you can put a little antenna on the thing, and you can go around to, like, let's say you got some noise that's just wiping out 20 meters. With spectrum analyzer, portable ones, you can go out there, you can go to the power pole, you can go to your neighbor's grow lights, you can walk around the house, see if you have a wall wart that's spinning off a whole bunch of hash. That gives you the ability to take and track down that problem in the spectrum of where you're experiencing, in the frequency of where you're experiencing that RFI. So one of the things that's kind of sad with the low-end spectrum analyzers, typically they don't include a tracking generator. Now, and I haven't got into, there's a bunch of different low-end type of spectrum analyzers. You have one that's just look very much like a VNA, the little VNA out there. You have ones that look like, actually it's a USB device. It doesn't have a head or a display on it at all. Use your computer to look at things. So some of those, like the USB guys, they have a P2 port, which will give you a output that will give you the ability to track it. Problem is that usually that P2 port is pretty low in output, and unfortunately that device doesn't have a whole lot of dynamic range, and so you may not get the desired response that you would hope to get out of it. So, but I'm still going to cover tracking generators because it's really an important part. So it's a signal source whose RF output follows the tuning of the spectrum analyzer. So that spectrum analyzer, if you're, going, just scanning the 80 meter band from 3.5 megahertz to 4 megahertz, that output port is going to produce an output at that same frequency, and it's going to track that sweep. Typically, that goes out on port 2. It's a two-port device. Port 1 is always your input. Port 2 is your tracking generator. If you want to take and figure out what's going on on a filter, this is typically what you would end up connecting up to your one end of your filter, and you'd connect port 1 and connect up to the other end, and you could look at how that filter, that bandpass filter, is maybe working. So, but on a true tracking generator, the output is calibrated in dB, and it's normally adjustable. So you can adjust whatever you want for the output of that. allows a signal to be applied to a device under test. So anytime you see DUT, and that's one of those mythical terms out there, it always stands for device under test. So it's a filter, if it's a piece of coax, if it's a connector, DUT is always that device under test. So there you're going to be measuring the frequency response, the attenuation. If you have, you may also looking at an LNA, a low noise amplifier. So you could also be looking at gain on what's going on. So that's a device under test. So measure performance of filters, high pass, low pass, band pass filters, tune for mixers, filters, cavities. So if you're doing like a repeater, you always have those cavities for both mixing and filtering. And your good old spectrum analyzer, that's incredibly important for doing that particular calibration. For coax measurements, like if you're looking at velocity factor, losses, some of them have the ability, and this gets a little bit more into the more expensive one. You're not going to find this in the lower cost ones. And that's, it does a time domain reflectometer, which allows you to look down a piece of wire or cable or coax and look for breaks, faults, splices, termination problems. You can actually determine the actual length of the coax. But the nice thing is that it gives you a graph up there, and you can actually see where you have little defects. You may have a kink out there, and surprising enough, in that graph you'll be able to see where that darn kink is. So this is something usually reserved for the a little bit more expensive spectrum analyzers. The nice thing about all of this is that this really provides a really nice, visible, high level, high quality accuracy, and gives you a great display, a great picture of what's going on. So why do I need a spectrum analyzer? So let's go back to, you've heard me talk about the ARL Clean Signal Initiative. So I'm sure everybody's heard about CSI. That stands for Clean Signal Initiative. And they're trying to do something. You know, they've done a huge amount of work on cleaning up our receivers and getting some really phenomenal receivers, but they haven't done anything to clean up any of our transmitters. So this whole initiative is out there trying to do more work to get us better transmitters that if on sideband it's supposed to be a 2.7 kilohertz bandwidth, it makes sure that we stay in 2.7. If we're running FM, it's supposed to be a 5 megahertz bandwidth. It makes sure that it sets in there. Also for intermodulation distortion, they give you lots of information as far as what's going on for IMD. I think everybody by now have heard me talk about IMD. Typically what gets stated in specification is cherry picked the best band, the best frequencies, giving the best IMD. It doesn't tell the whole story. You need to know what the IMD value of every single band, because there are different band filters that get loaded in when you flip between bands. And you want to know the IMD at the top of the band, and at the bottom of the band, and at the end of the band. So those are kind of statistics and numbers that we need to know in order to make quality selection of our ham equipment. So having said all that, so what happens if your mic gain or your compression is set too high? So we all know and hear about splatter and all the things that causes there. So it'd be nice to be able to look at your rig, take your mic gain, crank it up to the point where you know you can see with your spectrum analyzer, see that you're starting to get distortion and maybe even splatter. But it's nice to know what is that upper value on that knob or on that menu setting on how far you can go with your mic gain and your compression. So those are all things you can write down, and you can become a better operator by knowing what the limits are on how to operate that piece of equipment. If you're running an amp, got clipping and splatter, Same thing. Are you driving it too hard? Are you over modulating it? Is it you have a bad set of filters in there? So you want to know the same kind of information for your amp. ALC. So ALC, if it's properly implemented, all it should do is drop your output. But I keep hearing guys talk about sometimes it also, when ALC kicks in, it can also cause distortion. I haven't seen it, I haven't experienced, but this also gives you the ability to connect everything up, and when running ALC, and you can adjust that knob and determine when you're driving that thing too hard. On a tube amp, when you drive it too hard, your grid current is going to go up. When your grid current goes up, that's a very good possibility that you're going to start melting your plates in that tube. So having ALC set properly is going to save your amp, and this helps you understand your output power and knowing when that ALC kicks in to take and not let you further push the power to cause any damage to your tubes and amps. Looking at your FM and single sideband, I've already talked about that. That helps to make sure that you have good clean signals, your bandwidth is proper, and you're not getting any splatter or over modulation out of it. So again, it can also help you hugely when you're running power, because when you run power, you just never know what's going to end up popping up. And this guy will help you take and find those kinds of problems and trying to reduce or mitigate some of those things that happen. So why do I need the spectrometers? Okay, in my neighborhood, let's say this is more talking about interference. So in my neighborhood, I have a neighbor that still is running a plasma display. I hope everybody doesn't have plasma displays, should be dead by now. But spectrum analyzer, because you know what bands is screwing up, it'll help you end up tracking down that guy in the neighborhood that may be running a plasma display or may have some grow lights, or in your house. If I know that I used to have practically no noise in here in the house, but over the years that noise has moved up at least a couple S units, and I need to go around and do some checks on all my wall warts and see who's making all the noise, or to figure out if it's my cat cables for all my networking, or where it's coming from, to try and isolate what's going on in the house. So tracking down power line noises, if it's a power line that's really only emitting stuff that's in the 80 meter band that's you don't see in the AM band, you can get out there with a spectrum analyzer and track it down to figure out what power line and pole is causing problem. And and before you report it, you need to come up with some hard evidence, and you also need that number that's stapled on the power pole. Can also look at the health of coax. Sometimes, like, one of the problems I keep running into, guys are talking about they have some intermittent problem, and they can't figure out what it is. So I can usually come along with a SWR meter and do a carrier on it, and usually twist one of the coax connectors and usually find the problem. It's usually in the connectors. But having a spectrum analyzer, if you're not really at a connector, it will kind of give you some ideas about other things that are going on, because a regular old SWR meter is not always going to tell you what's really going on. It just tells you that there is a problem out there. Okay, so let's look at some pricing. So somewhere between $60 to about $300, you can find usually a spectrum, one of these tiny spectrum analyzers, a lot better than paying up in the thousands. The problems with some of these guys is that they have limited dynamic range, and that means how fast they can run and how they can deal with really, really small signals. Some of these guys will only pick up signals down to maybe about a minus 80 dB. A decent tabletop guy can get down to 130 to 160, maybe 150 to 160 dB, get down to some really small levels. So sometimes, depending on what you're measuring, these guys may not have enough dynamic range for what you really want to do. But for a generalization, it does a pretty darn good job. I think all of you guys can remember back when we had the good old MFJ antenna analyzers. You know, they weren't very good, but they were good enough to get the job done. A lot of work as far as design work on antennas, a lot of troubleshooting. That was the gold standard for a long time. Then came this nano VNA that wiped out the old MFJ analyzer. And now for the spectrum analyzer, it's good enough. It's not super great, but it will tell you a whole lot about what's going on as far as your transmitted signal. And that's that tiny spectrum analyzer. So another one is that I think a lot of you guys probably have one of those SDR plays. That's an SDR radio. A lot of what goes into a spectrum analyzer is basically an SDR radio. So with that device, you can load onto your PC some neat software that is a spectrum analyzer. And you can run that SDR play as a spectrum analyzer and look at what the heck's going on. The interface is a little bit crude. It's a little bit challenging to know how to operate it, but usually after about 30 minutes of frustration, you'll finally get the hang of it. But it actually, I've used it before, and it does do a pretty reasonable job of capturing information and allowing you to take and analyze what's going on. So let's talk about some parts that you probably need. You know, like any type of test equipment or anything, there's always a few extra little things that you want. One thing, if you're going to be looking at RF, you understand that going down that cable, you got hundreds of, or if not thousands of watts going down there. So you need something that drastically samples that information and attenuates it. Over on the right-hand side, there's a sample T. And the two ends is where you connect your coax at. The guy that sticks out the bottom, that's a BNC connection. That's where you connect your sampler going back to your spectrum analyzer. Now understand that thing slides in and out to attenuate signals. There's a process you go through to calibrate that thing to figure out how much your loss is going to be on it. Now that's a $60 part. You can go to $200 to $600 sampling devices that are all calibrated, that are really cool, but all of those things cost money. This is one of the dirt cheap ways of getting into it. You're typically going to want some RF attenuators. Down in the lower right-hand corner, there's a couple of attenuators, because you can't always get that RF down into the level that you need to keep from destroying that. Understand, going into that device, they will tell you a spec. It can only receive a certain amount of power. It'll be expressed in dB. So if you go to, maybe it's a minus 10 dB is the best you can put in. Anything past that, if you move up to 5 dB or a full dB, just a plain dB worth of power, that will end up frying that instrument. That's a very expensive mistake. So you always want to think about these attenuators to get the signal down low enough to you so you understand it before you can take and set the amount of RF that you want to end up bringing into the thing. Some of these guys, like especially the RF play, you want to use a blocking capacitor. That's the little guy on the lower left-hand side there. And that makes sure that no DC gets into that device. That'll end up screwing that that device up. You probably want a handful of adapters, something from either like 259s to something to SMAs. A lot of the cables you use for doing your sampling and stuff are either SMA or BNC type of stuff. So you need some gender stuff to change things around. Every good ham has got to have a good dummy load. Dummy load is always your gold standard as far as a 50 ohm load, putting power into it, and that's how you make almost all your measurements. So you should already have that dummy load today. Calibration kit. That's usually a set of 3 slugs. One of them is a short, one of them is an open, and one of them is a 50 ohm load. That helps you go through there and calibrate that instrument to make sure that it knows exactly what these different impedance are throughout the frequency spectrum that you're going to be sampling. So this is just a good old list of things that your other expenses that go on to just buying the device. Some of the kits come with some of these same things, but maybe not all of it. It comes with a lot of, it'll usually come with a calibration kit and some extra cables and maybe a couple little gender benders for adapters. So let's wrap this thing up. New low-cost spectrum analyzers work pretty darn well, but they will get you maybe 80-85% of the way and get you some basic readings that you can tell if there's a problem or not, and help you to get a decent picture of how your transmitter is working there, or how to end up tracking down RF interference. When it comes to tracking down RF interference, the dynamic range is going to be the limiting factor, how well that thing receives tiny signals. So sometimes that can be a shortfall. How well does your transmitter or amp work? So, I gave you a whole bunch of bullet lists. For me, I like to know the upper limits and lower limits of where I can set my dials, my knobs, to know if I have a problem. So I know to keep my transmitter operating within certain limits as far as compression, mic gain, and such. And that's the next bullet too. So it goes along with dealing with your amplifiers. You also want to know your upper and lower limits on what might go on with your amplifier. So it's a cool device for tracking down RFI. So, and also it can help you end up tracking down problems with your coax there. So anyway, that's all I had this evening. Hopefully it's worthwhile considering as far as what if you want to maybe make an investment on one of these low-cost spectrum analyzers. It's not a perfect environment, but again, neither was that MFJ antenna analyzer. Any questions?
Thanks, Mike. That was there were several things I didn't know about that, especially when it came down to the RFI spectrum. I'm sorry, the RFI checking. That is something I did not know a spectrum analyzer could do.
Yep, sure can.
Just as a reference, our RNS in the office in Austin, I think, is still worth $100 grand. So there are still very expensive spectrum analyzers out there.
Yep. But that's for.
And you wouldn't believe the trouble the guy got in that blew that thing up, and it had to go back for service.
Well, you said it was a guy, so I guess it wasn't you.
It was not me. It was one of the hardware guys.
Mike?
Yeah.
On that note, the attenuators, I have a tiny SA, and I haven't really used it yet. I have, my Nano VNA, which I've used quite a bit now. But the tiny SA, I think I played around with it. I know one way you could use it to track down stuff is you can sort of like attach a wire to the input and then walk around and the wire will act as an antenna. So it'll pick up very low level signals, and you can actually see them on your spectrum analyzer. And that's one way you can probably look for RFI. I think that's what you were getting at, right?
Yeah, yeah, you can take that port 1 and connect up a little one of those little extension antennas. You can connect up a little like a Wi-Fi antenna. Actually, what you probably want is maybe look on the MFJ site and find one of those little extension type of antennas that you can extend and with if you need more signal.
Okay.
I actually have a piece of coax with a little coil,
Yep.
made on the end of it, which is really useful for if you are trying to find some RF in a circuit. So I can actually hover that above the circuit board and pick up RF off of the traces of the board to try and figure out where RF is going.
Oh, that's a good way. Yeah.
There's also kits that you can get that have little different types of antennas that have an SMA connector on it for near field evaluations.
Yep.
And I think it's like only a $20 or $25 kit that has all kinds of different kinds of antennas that you can use for something similar to that. But this is more or less for tracking down stuff in a circuit that you end up using it, but you can use it for all kinds of cool stuff.
If you are poor and it doesn't work as well, but if you are poor, which I guess these cheap SAs don't kind of negate this. A lot of oscilloscopes have an FFT function that for low frequencies and in the ballpark works okay. I'm not, you're not going to be using them for 440 megahertz or anything like that, but lower frequencies and less demanding applications, the FFT function of your oscilloscope can work. It works best for audio frequencies.
Yep. So, and in that subject there, for oscilloscopes that have, and my oscilloscope has an FFT function in it, but dynamic range sucks.
Yeah.
It's not good for tracking down radio frequency interference. It just doesn't have the dynamic range to do that. Also, another thing on like using antenna on a tiny VNA, if any of you guys been out and done any bunny hunting, you know about techniques that you can use. In fact, they usually build like a tape measure antenna. You can use that for tracking down. You don't care that the antenna is not resident, just as long as it gives you some directional information. You can use that for tracking down direction of where RFI is coming from. The other thing that you can use is body shielding. So you can take that antenna and place it up close to your body and then rotate around to where it's the strongest, then flip your body around to the opposite side and make sure that it's the weakest. So RF energy is not going to do very well going through a person's body. And by holding that antenna up close, your back of your whole body, that side of that antenna is going to be shielded from any RF getting into that antenna. So that's another way that you can use to try and get your directionality information for tracking down RFI.
Another useful thing for some of the SAs is my SA, and I don't have a tiny SA, I've got a bigger Rigel one that I got a few years back. But some of the SAs, you can set the tracking generator to sweep at 0 hertz, which means that you will just get a constant signal out of it. So you can use it as a signal generator, which is great for things like putting a known signal into your receiver. You can set it for, negative 50 dB, and then make sure your receiver is showing about negative 50 dB. And that's a useful thing to have if your SA has that feature to it.
Yep.
Oh, so Anna, how do you do that? I mean, how do you connect the receiver to the
Very carefully.
What
actually,
I mean,
with a
actually, yeah.
Because I was going to ask Mike about calibrated, measurements, using attenuators and all that. But if you could do that, you can set the output to a certain level and then feed that into your receiver. How would you do that?
Use a cable just like anything else. The thing you need to watch out for is usually most tracking generators aren't going to create enough signal to blow up your receiver or anything. That's not what you're worried about. What you're worried about is most amateur radios, the antenna port both transmits and receives. So you want to make darn sure that you don't transmit 100 watts into your signal, your tracking generator, and blow it up. It's the other way you have to worry about.
Okay.
So usually, I mean, I think my tracking generator and my SIGGEN does like, maybe 5 dBm or something like that, which isn't very much at all. So yeah, you don't need to worry about it in the receiver. There are, I'd put attenuators in it because otherwise you end up overdriving your receiver to measure those signal levels, but you usually don't worry about damaging it. And if anybody wants, I can probably spare a few if anybody is really interested and wants attenuators, little inline attenuators. I have a bunch of them that I got surplus for free for different values. I might be able to share some of those. But no, I mean, I do it all the time where I hook up, radios to the SA or to, cabling things up between one another to try and test out what's going on.
You can calibrate your S meter that way
Yeah.
too.
Mhm.
Because a lot of them aren't calibrated really.
A lot of times when we're building a radio, there will be an exciter port inside of it. It's on some of the first board spins so that we can get into the output directly off of the ADC without any amplifier in it and make sure that we can test that and make sure it works. If you're using a radio that has one, you can also use a receive only port, and that makes it really safe, or a transverter port. When we test out all of our flex radios back to back or something like that, we end up using the transverter port to connect them together because there's little risk of blowing anything up in the transverter port. It's low level. But if you're running one of those cruddy IC7300s, then you'll have to find some other way to do it. They're like roaches, I tell you, roaches.
No meeting is complete until we've gotten shamed by Anna. Receivability and the filtering capabilities of the Flex.
They also make nice inline attenuators that are big. We have some that handle 100 or 200 watts that you can put through, where, they may only be a 10 dB attenuator, but they can handle power, right? So that it can dissipate 100 watts power and drop it by 10 dB. So much test equipment to buy.
Yes,
It's a dangerous path to go down.
it is. And it is. It's like when you get started on asking questions about what's going on with your transmitter and your audio and stuff like that, that spectrum analyzer is it's a rabbit hole as far as questions and answers. But as you go through there, it's really important to be able, and like virtually all these spectrum analyzers, even the tiny stuff, has the ability to connect it to a PC and save all those images off. And it is so important to go through there and document what the heck you're looking at, what you're seeing, and what all your settings were. So that's
a lot of the bigger stuff has Ethernet on it now. So my SA's got Ethernet on it. My power supply's got Ethernet on it. My SIGGEN has Ethernet on it. So it makes it pretty nice for working with stuff from your PC or your Mac to control stuff and turn it on and off. So the great thing for ham radio operators these days is most test gear, there's inexpensive stuff out of China that is good enough for ham usage, but is relatively inexpensive. You can buy I think I bought my dual channel 60 megahertz signal generator for $325. So,
Yep.
and that's, I mean, it's been worth its weight in gold over time.
Yep. Bye,
Looks like
Ted.
Ted's signing off.
Sorry, I could go off
So-
all day on test gear. I have a serious test gear addiction. Which, if you'd like some older Tektronix stuff, there's stuff in my garage that I would totally be willing to part with.
Nope. No
No,
boat
it does.
anchors.
Well, boat anchors could be useful still.
I don't have room anymore for boat anchors.
Hmm.
Depends, yeah, depends what you're doing.
Very
There's
good.
only
Nice topic, Mike. This has been, fabulous. Does anybody have any other questions on this topic? I'm sorry if I cut somebody off. I'm having a delay over here.
I'm
Well-
just going off incessantly like I usually do, so please feel free to stop me.
Scott, it looked like you had something.
Well, I would just say a nice follow-up presentation would be actually a demonstration. I think one of the most useful things you'd want to do is probably look at the output of your transmitter. So you figure out, let's say you buy a tiny SA, can you use that? And the question, so how would you connect it with attenuators? And then what are you going to look at? And how are you going to modulate or what are you going to do to feed a signal into your audio signal, let's say, and into your transmitter and look at the output for IMD and distortion and everything else. I think it would be very interesting. I mean, if you've got a higher end, like Flex, obviously you don't have to worry about that kind of stuff. But if you got like a little ICOM 706 kind of a thing, you want to see what it's doing these days.
I think
interesting.
that's like a semester's worth of class
You think?
for all those things you're asking for.
Yeah, I don't think so. I think that could be, with the right equipment, you can just kind of slap something. Well, not slap, but you can put something together and say, "Hey, this is how how you do it," kind of a thing.
Sounds like you're in charge, Scott.
Yeah, I guess I am.
If you're saying it's easy.
Put my foot in it. Yeah, well, I wouldn't mind. If I can manage it, I'll do it. It'll be fun.
All right, we'll expect to see some live demo at POTA. We have outlets.
Okay, so
Okay.
one other final thing is that next month, it looks like I will not be around for the meeting. So anybody that wants to put together a program, that would be seriously appreciated.
Yeah, I would be willing to do that, Mike, and maybe do follow up on yours with a live demo. Not live, but some sort of a demo to show the power of these things.
Mhm.